Hi everyone. So this is the solutions for page 56 to 59, drawing the force diagrams. As always, if you want to actually learn something as opposed to just making sure your book's full of answers, you need to attempt everything first. Even if you get things wrong, if you've attempted them properly and had a good think about them, then seeing the answers, you're going to learn a heck load more than nothing. So that's just, don't be lazy. Do some thinking yourself and then check these answers. As I go through them, the things I think about, the types of forces, just kind of 5 forces we need to worry about: gravitational, electromagnetic, normal force, friction force, and tension forces. Right, so I've done one as an example already. Let's go through the rest of these. So a force diagram for the skater is moving at a constant speed, or she's moving at a constant speed. So that immediately makes me think that the net force is 0, and I've been told there's frictionless ice. So label a force diagram for this. Right, here we go. First thing I do is identify the system. It's the ice skater. Then I redraw it as a dot. Then I draw my forces on. The obvious one is gravity. Force of gravity on skater by Earth. She's not accelerating downwards, so she must be balanced out. Force normal on skater by ice. Those are equal. The question is, she's moving forward. Is there some sort of forward force? What have we got here? We've got a normal force, a friction force, and a tension force. Well, there's no rope pulling her forward. Friction would oppose motion. Traction's like grip, but haven't we been told that it's frictionless ice? Okay, so we don't have that. The normal force is 90 degrees to a surface. We've already got that, 90 degrees to the surface. So there's no more contact forces. There can't be any contact forces pushing her forward. Non-contact forces, things that don't touch her. Well, there's gravity. We've already got that. Electromagnetic, she's not being pulled by magnets or anything. So I think that's it. Now, I know some of you want to draw something like that. This is a common mistake in physics, that they think that because she's moving forward, she needs a forwards force. Okay, she's moving at a constant speed. And if we go back enough, remember, constant velocity, the forces must be balanced. This means that the net force is 0. Because we have frictionless ice, there's no force going backwards. Because there's no force going backwards, to balance no force, we have to have no force going forwards. A force diagram for a softball player who's slowing down, or it's been given up here, slowing down as she slides into base. Okay, so identify the system, draw it as a dot. I'd like to start with gravity on person by Earth. She's not accelerating downwards, so there's a normal force by on person by ground. Those are equal and opposite. And if I was to draw, well, she's moving this way. So if I was to draw a motion map, she's slowing down. These are my velocities. So my accelerations in between are going back. So that means that I need, my overall force has to be going that same way. It's meant to be horizontal. And what could be slowing her down? Well, obviously friction. Air friction on person by ground. Cool. Force diagram for the chandelier. Suspended, not moving. Okay, so my system is the chandelier. What have we got? We've got gravity's, I can't spell chandelier fast, so I'm going to say on light by Earth. And there must be something pulling it up, and you can see the thing that's physically pulling it up because it's in contact, right? That's the chain. And chain is a type of tension force. On light by chain. And those are equal and opposite because it's not moving, not accelerating. The bucket of water is being raised from the well. Here's the key: constant speed. What does that mean? It means net force equals 0. Force diagram for the bucket of water. Identify the system. Just the bucket, not the person, not the rope, just the bucket. Redraw it as a dot. Force down, obviously, gravity. On bucket by Earth. Upwards, you can see the thing that's providing the force tension. On bucket by rope. Is the tension force meant to be bigger because it's going upwards? No, it doesn't matter if it's going upwards. It doesn't matter if it's being raised. It's being raised at a constant speed. So these must be the same. Even though you can say, well, that's the same as the chandelier that's not moving. Yes, the key is constant speed is no net force. At some point, I agree, way down here at the bottom of the well, when the bucket was at the bottom, the man had to get it going. He had to accelerate it. It was resting, and he had to speed it up. And when he got it going, then without a doubt, it would have had a bigger tension force than gravity force. But now it's going at a constant speed. This is the answer. A skydiver has just left a plane and is speeding up. Okay, so let's do this skydiver. Left the plane, so falling, speeding up, must be a net force. F gravity on diver by Earth, and maybe he can feel a little bit of friction. I always, if I ask myself, is the air resistance, friction by the air, I always think to myself, can I feel it? Like when I'm on a bike going slowly, I can't really feel the air in my face. When I'm coming down a hill really fast, I can feel the air on my face. And when I can feel it pushing my face and blowing my hair around, then I'd say it is providing some friction. So F friction on diver by air. And it's a small error. A skydiver who's descending at a constant velocity, label all forces and use equality marks on the force vector. Okay. So I'm going to do this two ways. The first way, I'm going to choose the system to be just the man. So he's descending at a constant velocity, his parachute's out. Of course, he's got gravity on man by Earth. And what's pulling him up? Air resistance isn't pulling him up. These ropes are pulling him up. So he's got a tension force on man by parachute. Those are equal. The second way I'm going to do it is I'm going to, here's the man, here's parachute. I'm going to do the whole system. Both the man and the parachute as my system. In that case, gravity on system. I could have called it man and parachute, but I'm just going to call it system because it's shorter, by Earth. This will be slightly bigger than this one because it's now the gravity's acting on the man and the parachute. The whole system's still moving at a constant velocity. So these must be balanced out. And in this case, yes, on the system, it's the friction on the parachute, on the system, I'd say on the parachute, by Earth. No, by air. So that's two ways of dealing with it. You get a slightly different answer depending on what you choose as your system. Number 8, force diagram for a ball rising in a parabolic trajectory. Label the forces. So at some point someone kicked or threw the ball. When it's rising, even though it's going this way, what do I know? First of all, I know that I need to identify the system. I know there's definitely gravity on ball by Earth. Of all my other forces, gravity, electromagnetic, friction, tension, and normal. Normal is 90 degrees to a surface. There's no surface touching it. Tension is from a rope. There's no rope touching it. Friction is from something grabbing it and slowing it down. There is a little bit of air, but on a ball I don't think it's going to be much. I might put that in. It'll be going against it, like that. F for friction on ball by air. We've got gravity and there's definitely no electromagnets anywhere. Okay. Some of you want to say there's some sort of kicking force or thrusting force or something like that that makes it go up. Not there. Okay. Forces are, by definition, interactions between two objects. At one point, when the ball was touching the foot here, they were interacting, the foot and the ball. When they are no longer touching, they are not interacting. Another little rhyme that someone in my class in Australia once said was, apart from gravity and magnets, if there's no touchy between the two objects, there's no forcey. I like that one. No touchy, no forcey. The foot is not touching the ball, therefore no force from the foot. Right, the ball is now at the top of its trajectory. It's going up, and it's a parabolic, so it'll go down like this way. So it's still moving, even though it's at the top, it's still moving to the sideways a little bit. Same deal. If we go through the forces, well, first of all, we'll identify the system. Must be gravity on ball by Earth. And what else? It's still moving. It's moving up here, and as it goes across the top, it's still moving that way a little bit. So there's going to be a little bit of friction on ball by air. Now I know what you want to do. You want, I can feel it in your bones, that you want to put some sort of upwards force on this ball. I don't know what you want to label it. And this is where it's so powerful when you label forces like I have. So if you say, well, there's definitely a gravity force, but there's definitely some upwards force. Let's call it a normal force, right? If you just put that, you could be wrong and not realize it. But if you go through the process of labeling it and you say on ball by what? What is the thing pushing it upwards? As soon as you get to this, because you've been writing it out, you realize, and you realize it doesn't exist. Okay? Right, the last ones are extension questions. They're optional. So I'm just going to go through them. Yeah, now. You didn't need to do them, but here are the answers. A cork's floating in the water. It's pretty easy, but it's just about using our labels. Gravity on cork by Earth, and F normal on cork by water. They're the same size. You can put 2 equalities. You can even get in the habit of putting 3 if you want. You can do what you want as long as they're the same. Aeroplane, straight and level flight. Okay, identify the system. Airplane's a tough one, but we'll get there. We know there's always gravity. trying to pull it down. If the wings fell off, it would fall out of the sky. On plane by Earth. We know there's friction. If you put your head out the window, you could feel the air pushing your face pretty hard. Let's make this big. If on plane by air. Okay, how does the plane work? The engines have propellers, they spin around, and what they do is they push air out the back. They physically push air molecules against the propeller. That pushing of the air molecules backwards pushes the plane forwards. Okay, just like when you sit on a seat, here's my seat here, here's my person, they're meant to be touching. There's physical molecules that are pushing against you because they've been squashed. That's the normal force. Here, molecules are being pushed backwards, just like your bum pushes these molecules downwards, and they want to push back. These molecules push back on the propellers, that what makes it go forward. So in year 11, you called this the thrust force. When you look at it microscopically, you see it's just another normal force with air molecules. It's a normal force on, we'll say on the propeller by air, and those are the same. How does it stay up? The wings, you can see them bent in this way, are such a way that air comes and gets hit downwards. Right? As the air gets pushed downwards, it pushes the plane upwards. Just like when we sit on a chair, when we sit on these molecules and we push them downwards, they push our bum back upwards. So the air is flowing along, or the plane's flowing into the air and gets pushed downwards by the shape of the wing. So that's another, and that pushes the plane upwards. That's another normal force. That's F normal on wing by air. And that's the same size as that. It's a tough one. You used to call these forward forces a thrust, and you call the upwards force a lift. Those are good words and they're fine, and you'll see them around. The issue with using thrust as a force is that people just want to add it in as any force. Remember the ice skating example? Here's my ice skater on frictionless ice. She doesn't have a forward force. She's just gliding at a constant velocity. People want to draw in a forward force. They can't think of a name for it, and this is the one they pick. So that's why I don't like using thrust. I like looking at microscopically what's happening to the particles and just labeling things with the 5 things: normal, friction, tension, gravity, electromagnetic. Right, a nail's been picked up by a magnet. It's sitting there, not moving. Now we can use them finally, if we identify our system, we can gravity on nail by Earth, and we can finally put in our electromagnetic force on nail by magnet, and they're the same size. Great, good job.